Hai, Assalamualaikum dan salam sejahtera. Welcome to another edition of the Physics Unmasked video series. In this video, we will continue with another aspect of the refraction of light. That is the total internal reflection and dispersion. Previously, we have seen that when light propagates from a dense medium to another optically denser medium, the light refracts and bends toward the normal line. This bending toward the normal line is true at all incident angles. However, when light propagates from a denser medium to a less dense medium, the light refracts and bends away from the normal line. This latter property is what we want to study now. We shall look at the simulation next. The light ray begins from a denser medium and propagates toward less dense medium. The light ray refracts or bends, but now the bending is away from the normal line. As the incident angle is increased, the light ray bends more and more away from the normal line, and the light ray refracts closer and closer along the boundary between the two mediums. When the incident angle is further increased, refraction into the second medium completely vanish. Instead, the light ray is reflected into the medium from where it came from. This effect is called total internal reflection. Let's analyze this properly and see how can we see if there is a relationship or rule that we can derive from this phenomenon. If you have noticed in the simulation, there is a special angle by which when the incident angle exceeds this special angle, the light ray will no longer propagate and refracts in the denser medium. Instead, total internal reflection occurred. Let's analyze. Okay, let's analyze this situation where the light beams or the light ray begins from a denser medium, glass, toward less dense medium, air. Now, as long as the incident angle is smaller than the critical angle, we can see that the light ray diffract away from the normal line in the second medium. Now, if the incident angle is greater than the critical angle, you can see that the light ray now reflect back in the first medium. So this is where the total internal reflection occurred. Okay, now we'll try to focus on figure B. This is a special case where the incident angle is exactly equal to the critical angle. And we can see that the light ray reflect at 90 degrees angle from the normal line. And we will begin the analysis by applying Snell's law so that if we can come out with a relationship between the index of glass with the critical angle. From Snell's law, n1 sine theta 1 equal n2 sine theta 2, where in our case, n1 is the refractive index of glass, theta 1 is the critical angle or the incident angle, now becomes the critical angle, theta c, n2 is the refractive index of air, and sine 2 is the refracted angle, which is equal to 90 degrees. So that we have sine theta c equal n2 divided by n1 multiplied by sine 90 degrees. And we can write the critical angle, theta c, is equal to the sine inverse of the ratio of n2 over n1. And this expression for critical angle is always true, provided that index of refraction n1 is greater than index of refraction n2. So in our case, index of refraction for air is equal to 1. And let's just call index refraction of glass N1 is just N. And that will make our expression for critical angle theta C equal to sine inverse of 1 over N. So this last expression give us or allow us to determine the critical angle of glass in air if we know the glass refractive index. And please take note that theta C is the critical angle and N is the refractive index of the medium in air. A word of caution here in the use of this last expression for critical angle, because if the medium outside glass is other medium than air, the previous expression is valid. In other words, if the second medium is other than air, but still N1 is greater than N2, then use this equation to calculate the critical angle. Next, we shall now look at some examples where total internal reflection happened naturally or being applied in some optical instruments. First, a simple experiment that you could do at home is shown in the slide here. The aim is to demonstrate that light ray bends along the shape of a falling water spout as a result of total internal reflections. We have a small hole punched on one side near the base of the bottle. The bottle is filled up with water and the water will now flow out, sprouting from the hole. Using a small pointing laser placed at the opposite side of the bottle, we try to shine the laser toward the hole. This may take several trials before we get it right. It is important to get the laser hit the hole directly so that we can see the effect of light bending more clearly. Right there. See, you can see the laser light bends following the shape of the water flowing out and falling to the ground. Okay, let's take a snapshot of the video. What happens here is that the light ray, which originally traveling straight, encounters the water-air boundary at the curved path of the falling water. And it so happened that the incident angle the ray makes at the water-air boundary is greater than the critical angle. As a result, the light undergoes total internal reflection and bends within the water column. At another water-air boundary, another total internal reflection occurs, and the process repeats until the end of the path of the falling water. Figure on the right is showing roughly how the ray travels in the water spout. Binocular is an optical instrument that makes use of total internal reflection within its prisms. Actually, the primary use of prisms is to correct the inverted image produced by objective lens. At the same time, however, the total internal reflection helps to fold the light path so that binocular can be designed in a more compact size. The picture on the right shows some light rays entering one of the prism inside the binocular. It can be seen that the light rays undergo total internal reflection on both sides of the prism. As a final example, total internal reflection also occurs in the formation of a rainbow. But before we go into detail about the rainbow, we want to discuss on the dependency of index of refraction on wavelengths of light. Recall that in the previous video, we have seen and understand that the index of refraction of refracting medium is equal to the ratio of speed of light in vacuum to the speed of light in the medium. And in another relationship, the refractive index is also equal to the ratio of wavelength of light in vacuum to the wavelength of light in the medium. Therefore, the index of refraction of a material depends on wavelength or color of the light. In another word, for a given material or for a given medium, as shown in the table here, the index of refraction varies with wavelength or color of light passing through the medium. As shown in the table, the index of refraction of borosilicate crown glass has a value of 1.509 for red light and 1.521 for violet light. The dependence of wave speed and index of refraction on wavelength is called dispersion. Now you may wonder, how does the dependency of index of refraction on wavelength affects the refraction of light in general when the light passes or propagates through a medium? Perhaps we could mention here the classic prism experiment by Isaac Newton in 1671. In that experiment, Newton demonstrated by his experiments with prisms that white light consists of a mixture of 7 colors. Newton was able to conclude at that time that pure white light was composed of 7 visible colors. Just as shown here, when we pass white light through a glass prism, the white light separates into spectrum of many colors. We normally associate only 7 distinct colors in the order of violet, indigo, blue, green, yellow, orange, and red. It also shows that different wavelength or color is refracted or bent with different amount. In fact, we can use Snell's law again to prove that violet light is indeed refracted with greater angle of refraction than the red light. The slide here shows the dispersion of white light by a prism. Note that the red light having the longest wavelength is refracted the least. The violet light having the shortest wavelength is refracted the most. Okay, as a summary, we know now that in glass or any medium other than air, different colors or wavelength of light travel at different speeds. The splitting of white light into its constituent colors during refraction is called dispersion, and the band of colors formed by dispersion is called a spectrum. An early morning stroll on a field. This group of people was lucky enough to be able to stand in a field with a rainbow in the background. What a nice shot, because the rainbow captured is almost full half circle. A rainbow is an excellent demonstration of the dispersion of light and an evidence that visible light is composed of a spectrum of wavelengths, each associated with a distinct color. Rainbows result from combination of refractions and total internal reflections of sunlight in falling water or falling rain droplets. A simplified diagram of a rain droplet and a light ray path through the droplet is shown here. What we have here is a light ray from the sun enters the droplet and refracts or bends. It then hits the back of the droplet and undergo total internal reflection, and then exit the droplet as a band of color spectrum. Okay, that's all we have for this video series. But before we end, let us summarize some of the key concepts that we need to understand and remember in order to explain and appreciate the properties of light when it propagates from one medium to another. When a ray travels in a medium of greater index of refraction toward a medium of smaller index of refraction, total internal reflection occurs at the interface when the angle of incidence exceeds a critical angle. Critical angle is an incident angle that corresponds to the refracted angle of 90 degrees. In general, the refractive index varies with wavelength. The dependence of wave speed and index of refraction on wavelength is called dispersion. Okay, till we meet again in the next video. Assalamualaikum and bye-bye.